Alrighty, welcome to module 3.9. This is our last module for this unit, and we're going to be looking at a few things, including the rate of reaction. So let's jump straight into this. So the first thing we're actually going to talk about today is something called the mole. Now, I'm just going to backpedal a little bit here. I want you to think about the word a dozen. What does it mean? When I say that, it probably box of eggs or carton of eggs pops into your mind, and you know quite specifically that that means 12. Generally, we talk about a dozen eggs because they come in 12, and half a dozen would be 6. But we might use another term that's kind of similar, like a baker's dozen. You might have heard that before. That means 13. And so they're both these sort of words where we use a word to represent sort of a bit of a weird number. Well, I'm going to throw in a new one here. It's called a mole. M-O-L-E. Now, there's lots of different ways we might talk about the word mole and lots of different meanings it has in chemistry. However, it is a word that means a specific number. So what was done is they looked at 12 grams of something called carbon-12, and the number of particles, the number of atoms of carbon-12 in those 12 grams was called a mole. Now, that number is approximately 6.02 times 10 to the 23. So it's a very, very big number. That's basically a 6, 0, a 2, and then 21 zeros after that 2. So to save ourselves time, instead of writing that out, instead of even writing 6.02 times 10 to the 23 every time, we can use moles instead. It's a bit like instead of writing 12 every time, you just might write 1 dozen or something like that. It also has another name. It's known as Avogadro's number, after Avogadro, a scientist who was involved in sort of the development of it. Now, it's a number that you can use to describe maybe how many atoms there are on something. You could use it to describe how many molecules. You could use it to describe how many ions or even electrons. I mean, if you wanted to talk about how many grains of sand there were or something like that, you could use it. It's just a word meaning a specific number, and you can apply it to a variety of scenarios. We do tend, however, really only to use it in sort of this area of chemistry. Now, if you have 1 mole of something, that might be carbon, it might be nitrogen, it could be hydrogen, it could be gold, whatever it is. If you have, we'll say gold, if you have gold and you have 6.02 times 10 to the 23 atoms of gold, the amount that weighs is what we call the molar mass. Okay, for gold, that happens to be 197 grams. So if you had 6.02 times 10 to the 23 atoms of gold, it would weigh 197 grams, and that is its molar mass. When you're looking on the periodic table, you'll notice you've got a couple of numbers there. Normally you'll have going up by 1 every time the atomic number. So hydrogen's 1, helium's 2, lithium's 3, beryllium's 4, and so on and so forth. But you'll also have another number, and that number, with the exception of what it is for hydrogen, but that number pretty constantly is always bigger than the other one. It's the bigger of the two numbers. That second number is your atomic mass, and that really is what we're talking about here. Now, that is just for an individual element. You can also talk about molar mass for molecules, and we'll look at that in a little bit and how you can actually calculate that out. For now, I actually have a video here that goes a bit more into explaining the mole for you, so we'll watch that now.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it. The story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
Alrighty, hopefully that clarified things a little bit further as well. What I want to talk about now is actually how you can work out how much something will weigh if you have 1 mole of it. And that might be of a single element, and that might be of a molecule. So you do that by adding together the individual masses of the atoms in that molecule. So we have a couple of examples here. You can see we've got NH3, and if you look on your periodic table, I would recommend, if you don't have one, looking up the periodic table that's used in the VC chemistry exam. It's a really nice and clear one, and it's got really easy to use values in it. So you can see there that nitrogen is 14 and hydrogen is 1. So you've got 1 nitrogen, so you've got that 14 there, but you have 3 hydrogens, so you have to go 3 times 1. So you add them together and you end up with 17. So that's example 1. Example 2, you have NaNO3, and if you look in the brackets, you can see Na is 23, N is 14, O is 16. And so if you go through and add them up, you can go 23 plus 14, but you've got 3 oxygens, so you'll have to multiply that 16 by 3 because you've got 3 of them in the molecule. And if you do all that, you'll get 85 grams per mole. Grams per mole is the units we use for molar mass. Alrighty, so I have here some molecules for you to work out the mass of the following. Like I said, you'll need a periodic table for this. The VC chemistry exam one's the best. If you want to find it, you can just Google VC chemistry periodic table data sheets and periodic table, and it'll be in there. So find yourself a periodic table. If you get a different one, your values may be off by a few decimal places. It's not the end of the world. It just means you might be using a more precise or a less precise periodic table to do this. But find yourself a periodic table, sit down and have a go at these, and pause the video now. Alrighty, so let's go through the answers for these. I'm going to do them one at a time, and I'll have to clear the screen after each one. But let's start with sodium chloride. So I'm starting with NaCl. And so if we think about it, Na and Cl are the 2 molecules we've got. We need to know how much each of them weigh. So Na, sodium is 23, chlorine is 35.5. So if I've got NaCl, the molar mass of that is going to be 23 plus 35.5. I only have one of each, so I don't need to do any multiplying in here. And if I add those together, I get 58.5. Alrighty, so that is sodium chloride. So if I had 6.02 times 10 to the 23 molecules of sodium chloride, it would weigh 58.5 grams. Okay, so let's jump in to the next one, and that is water, H2O. So H2O up there. So we need to know what the mass of hydrogen is, what the mass of oxygen is, and then we're going to work out the molar mass of water. So hydrogen is 1 and oxygen is 16. So down here, what I'm going to do is I'm actually going to, in brackets, I'm going to say, okay, hydrogen's 1, but I have 2 of them, so I need to multiply that by 2, and I'm going to add that to 16 for oxygen. So 1 times 2 is 2, plus 16 for oxygen, so this is going to be 18. So the molar mass of water is 18 grams per mole. And you can just write grams per mole like that. On the next one, I'll actually show you another way you can write grams per mole. So that is what it would be for water. Okay, so let's go to our third one now. So our third one is FeSO4. So we need to know the masses for 3 different elements this time. So we need to know for iron, which is Fe, sulfur S, oxygen O. And then we're going to work out molar mass of FeSO4. So iron is 55.8, sulfur is 32.1, and oxygen, like we already said, is 16. So what we're going to do, it's pretty easy for the first two because it's 55.8 plus 32.1. I'm going to have to go on to the next line here. Plus, and then this is where things get tricky, brackets. I've got oxygen is 16, but it needs to be times 4 because there are 4 of them. And so if we do all that and calculate it out, you should get 151.9. And this is how you'd write the other way, GMOL, and then a little -1. That's the other way of writing grams per mole. You don't need to, you can totally write it the other way, it's completely fine. They both mean exactly the same thing, it's just a different way of representing it. So that is the molar mass for iron sulfate. So that's 3 out of 5 done. Let's jump on to our second to last one, which is copper nitrate. So Cu bracket NO3 close bracket 2. Now, just quickly fill in the values for these. Copper, nitrogen, and oxygen. 16, that's 14, and copper is 63.5. Now, when you've got something like this with brackets in the molecule itself, you can go about it a couple of ways. You can work out how much what's in the bracket weighs itself, and then multiply it by that number outside the bracket. So here, I'd work out how much 1 nitrogen and 3 oxygen weighs together, and then I'd multiply that by 2 because there's a 2 outside the brackets telling me that there's 2 lots of that. Or you can just basically work out how many there are of every single atom, and you can just do it like we were doing before. So I'm actually going to do it that second way. So we're going to do molar mass of CuNO3 2. Okay, and I'm going to write down here, this would be 63.5 plus, now 14 for nitrogen. I have 1 nitrogen within the brackets, but there's 2 lots of brackets, so that means I need to go times 2, plus 16 for oxygen. Now there's 3 oxygen in the brackets, but there's 2 lots of brackets, so it's 3 times 2 is 6, so it'll be 16 times 6. All right, if you work that all out, you should get 187.5 grams per mole. Alrighty, hopefully you were able to get that one. So that is how you get it for copper nitrate. Now that one is a little bit on the trickier side, but if you are wanting to move on to something like VC chemistry, you will need to get comfortable with doing those kinds of ones as well. Alrighty, so let's get rid of that. And we will do, lucky last, C6H12O6, which you may or may not recognize actually as glucose. So C6H12O6. 6. So carbon, hydrogen, and oxygen, CHO. Now go backwards, this is 16, this is 1, and this is 12. So the molar mass of C6H12O6 is equal to, so carbon weighs 12, but there's 6 of them, so it's times 6, plus, not 12, 1 for hydrogen times 12, because there's 12 of them, plus 16 for oxygen times 6 as well. And if you were to work that out, that would be 72 plus 12 plus 96, which is equal to 180 grams per mole. Alrighty, and there you have it. That's how you can find the molar mass of different molecules. Now, you might be thinking, well, why do that? Well, because when you know the molar mass, you can also go back the other way and you can start working out things like how many moles you might have of something, which is really handy for doing some more complex calculations and reactions in chemistry. So let's have a look at how you can actually approach that. Now, if you want to work out how many moles you have of something, you can use this formula here. There's actually another formula you can use, but this one is dealing just with mass, and that's what we're interested in. So it's basically N means the number of moles. The number of moles is equal to however much you have of it, so whatever the mass is of your sample, divided by the molar mass. So for example, we've got down there, it says how many moles of calcium oxide is there in 3.2 grams? Well, we don't know how many moles, so N's our unknown. Little m is 3.2. Little m is the mass. Sometimes you might just see little m, big M. This also has, instead of just big M, it has MR on there, so you may see it one way or the other. But big M is always the molar mass. So little m is 3.2 grams. The big M for calcium oxide is, if you do what we were doing before and you add all those values together, you get 56.1 grams per mole. And so what you can do is if you take the 3.2 and you divide it by 56.1, you will get 0.057 moles. So that's how many moles you would have in 3.2 grams. So you wouldn't even come up to 0.1 of an actual mole. It would be way underneath having one whole mole. So if you want to know how many particles that would be, you'd take that 0.057 and you'd actually multiply that against this 6.02 times 10 to the 23. But that's sort of a step above. It's just for those who are interested in knowing it. That's what you would do. So we've got a couple of questions here. The first one wants you to find the mole of sodium chloride. If you have 500 grams of it, how many moles are there actually in that? And the second one wants you to go the other way. Well, what if you have 5.1 moles of potassium hydroxide? How much is that actually going to weigh? So what you'll need to do is you will need that equation, N equals M on molar mass. You'll need to use that to help you with this, and for the second one you will actually have to rearrange it to work it out, and you will also need to know how to calculate molar mass, so you've got to be able to do that calculation for that bottom number. Alrighty, so pause the video now and give those questions a go. Alrighty, so let's go through the answers for these two. So like I was saying, you're going to need to use that equation N equals M on MR. And for this first one, we're going to use it as is because we actually want to find out what the moles or what N is. So we're going to say we want to know what N of NaCl is, and this is going to be equal to 500, which is our mass, divided by the molar mass of sodium chloride. Now, we actually did this a little bit earlier, so you can just go back there and get it if you didn't have it, or you could recalculate it. So I've got it here in front of me. It was 58.5, and what I can do is if I divide 500 by 58.5, I get 8.55 moles. So there's 8.55 moles. In terms of how many actual molecules there are, that would be 8.55 times 6.02 times 10 to the 23. So that's a very, 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 very big number. So that is how you do the first one. As for the second one, we're going to have to rearrange that equation. So it's not going to be N is equal to M on M. You've actually got to bring the M on the bottom across to the other side, and so if you flip it around and rearrange it, you'll end up with M is equal to N times MR. So here we want to know what the mass of potassium hydroxide is. So that's going to be equal to the number of moles, which is 5.1 0.1 times the molar mass, or MR, of potassium hydroxide, which is KOH. Now, we haven't calculated this. If you go through and do it, what you get is 56.1. And when you multiply those two together, you are going to get 286.11 grams. So if you had 5.1 moles of potassium hydroxide, it would weigh 286.11 grams. So that's how we do those questions. So here is a few recapping questions on what we've been talking about. The first one, what is Avogadro's number? Do you remember it? What are the units that we use to calculate molar mass is number 2. What is the equation we use to calculate moles? And then you've got a couple of calculations there at the bottom to do. So pause the video, try and do as many of those questions as you can without going back and looking at what we've just been doing. But pause the video and give them a whirl. Okay, so let's go through the answers here. Okay, so Avogadro's number is 6.02 times 10 to the 23. Okay, it's the number of particles or something in a mole. It's that same number. The units to calculate molar mass, or the units that we give molar mass in, is grams per mole, or you could write that as GMOL with a little negative one. So that's the units. The equation that's used to calculate moles is N is equal to little m over mR. So hopefully you've gotten those first 3 right. I'm going to clear the screen and I'm going to start doing the calculations for the next 3. Okay, so the first one, question 4 is about calculating molar mass. So we're going to be adding a lot of things together here. So we're going to do Na2SO4 first. So I need to know for Na, I need to know for S, and I need to know for oxygen how much their molar mass is individually so I can add them together. So sodium is 23, sulfur is 32.1, and oxygen is 16. So the molar mass of Na2SO4 is going to be equal to 23 for sodium times 2, because there's 2 of them, plus 32.1 for sulfur, plus 16 for oxygen, and there's 4 oxygen, so you're going to have to go times 4. Do all that, and you should have gotten 142.1 grams per mole. Alrighty, so that is the molar mass of sodium sulfate there. I'm just going to do the other one down the bottom here, which is NH3. You need to know for nitrogen and for hydrogen. Hydrogen, hopefully you remember, is 1, and nitrogen is 14. So the molar mass of NH3 is equal to 14 for nitrogen plus 1 for hydrogen, but that's got to be times 3, so we'll do it like that. And this gives you 17 grams per mole. Alright, so that is the molar mass of those 2 there. I'm going to clear the screen and we are going to do our last one. So calculating the moles of water in 3.2 grams of it. So we need to use the N is equal to M on M equation. And so we want to know how many moles, number of moles of H2O in 3.2 grams. So it's going to, the mass is 3.2. That's how much we have of it. That goes on top. And the molar mass of water is 18. Remember, oxygen's 16, and then each hydrogen is 1. So you've got 2 of them. So 16 plus 1 is 17, plus another 1 is 18. So we'll do 3.2 divided by 18. And that gives you 0.1, we'll round to 1.18 moles of water. So it's quite a small number there. Alrighty, so that's sort of it in terms of calculating things with moles. We actually want to talk now about how quickly reactions happen. So the speed or rate at which a chemical reaction occurs can vary. Some reactions are really, really quick and they may occur in a fraction of a second, while others can take days or even years to occur. It depends on quite a number of factors. Now, not all reactions occur in timeframes we want them to happen in. So actually have a bit of a think. Would you like the following reactions to be fast or slow? What ones do you want to be fast, and what ones do you actually want them to happen slowly? So pause the video, have a bit of a think, and then have a think about how you could control the rate of those reactions, either slowing them down or speeding them up. So pause the video and have a bit of a think. Okay, so rusting of an iron bridge, that's the sort of thing you'd want to be slow, because the rusting's going to wreck the bridge. So we want that to happen as slowly as possible, if it has to happen at all. On the other hand, when we're baking bread and the production of carbon dioxide that gives it a nice fluffiness, you want that to happen quickly because you don't want the baking to take forever. Although there's lots of different things involved in making bread, and sometimes we do things to make it take a bit longer for things to develop. So that's a bit of a funny one. It can actually go kind of both ways. The oxidation of alcohol in wine and forming vinegar, well, unless you're intentionally trying to make vinegar, you tend not to want your wine to go off and turn into vinegar. So that's one you'd want to happen slowly. On the other hand, you'd want fuel to combust in a rocket engine very, very rapidly, so you actually get that lift off. And if you've had to take some painkillers, you're going to want them to work quickly as well. Now, how you can control these rates of reaction is really interesting, and that's what we're going to get into now. So, it's of great interest to chemists to be able to control the rate of a chemical reaction. You want reactions to occur quickly enough to be useful, but not so quick that they could be explosively dangerous. There's about 5 ways you can control the rate of reactions. You can, first of all, change the concentration or amount of the reactant. So those are the things going into the reaction. You can change the temperature that the reaction is happening at. You can change the surface area available for the reaction to take place on. You can add what we call a catalyst, or finally you could change the volume or pressure in the vessel, and this normally is something we reserve for gases. Not all the time, but that's predominantly where it's most useful. So changing the volume or changing the pressure something is happening under. That's sort of what pressure cookers actually use. So I have a bit of a fun video here looking at how each of those work. So I'm going to play that for you now.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student, and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk her to class. And you'll never guess who went together to the dance later that year. Yep, those two. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now, you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have 2 important characteristics. 1, correct orientation that allows books to be knocked from one's hands, and 2, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I propose 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I propose that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date to the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen. Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help make sure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth, students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small, and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased, and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is this colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? Then a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing two particles together and orienting them correctly in space so that the two can meet at the correct configuration and allow a reaction to take place. So, to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.
Alrighty, so let's just go through each of those now. So the first one is change in concentration. So if you have a dilute solution, the particles of the reactant are going to be really, really spread out in whatever you've got them dissolved in, which is probably going to be water. But in a more concentrated solution, there's a lot more of those particles and they're much closer together. And what that means is they're more likely to collide and actually have a chance of reacting with each other. So increasing the concentration allows for more particles to react, and they're more likely to collide, and when they collide, they're going to hopefully react. But if you want to slow something down, you might actually decrease the concentration because that's going to reduce the chance of particles reacting. One example might be when you're going camping. If you want to get the fire burning really, really hot, you might fan it, and by doing that, you're pushing more oxygen into where the wood is burning to help with that combustion reaction. So that's changing concentration. Changing temperature has to do with the idea that temperature is actually a form of kinetic energy. And so as things warm up, they move more. And so the higher the temperature, the faster the particles are going to move. If they're moving quicker, they're more likely to collide and interact. And they're also more likely to have the energy that they need to react in the first place. So our example here would be putting food in a fridge. We do that because there is chemical reactions that microbes do, and by putting it in the fridge, it slows those reactions down so food lasts longer. On the other hand, I can think of something you might put in the freezer to, it's not about preserving food, but it's actually about glow sticks. And when you crack a glow stick and it's got that wonderful reaction that glows, if you put it in the freezer, you can actually get your glow stick to last longer because it slows that glowing reaction down. It doesn't stop it, but it slows it down so it will actually go for longer. On the other hand, there's a lot of things we heat up so that they speed up. And those are the 2 ways we use change in temperature. Thirdly, you can change the surface area. So I think that video is really good at showing how changing surface area helps out things. But basically, the more surface area that's exposed, the faster the reaction is going to occur because of all the particles in your reactants, you've now got more exposed to the thing they're reacting with. So instead of having some particles shielded and unable to react initially, everything's exposed, or as much as possible is exposed, it's able to react. It's kind of like how when you've got sugar and you're trying to dissolve it in water, the sugar that dissolves in water the quickest is going to be your powdered or your icing sugar. Whereas if you had it in a big cube, it's going to take really long before it actually all dissolves in. And that's just because there's less surface area. And so there's sugar inside that cube that's being shielded, whereas it's not the same for powdered sugar. And so you've got another example here. It's talking about the reaction between a metal and hydrochloric acid is going to occur more quickly if the metal is in powdered form rather than as a metal strip. Powders have a much larger surface area on which the reaction can occur. So when bath bombs are added to water, the chemicals inside begin to dissolve. Now, what would happen if the ball was crushed into smaller pieces? You can pause the video, have a bit of a think, see if you can work it out. So, if you were to crush those bath bombs, it's going to increase the surface area so that there's a large area that's going to come in contact with the water. And as such, the bath bomb's going to dissolve way more quickly. So, if you ever have a bath bomb and it's sort of been fizzing for a bit and then you've got a little bit bobbing around the water and you're a bit annoyed and want it to go away, you can just crush it and it's going to dissolve a lot more quicker. The fourth thing we're looking at here is catalysts. Catalysts are really interesting substances. There's a wide range of them and you have them in your body. In fact, the ones in your body are called enzymes. They're in us, they're in plants, they're in animals. They're basically biological catalysts. Now, a catalyst, by definition, is a substance that increases the rate of reaction by lowering what we call the activation energy. But, and this is really important, but the catalyst isn't actually used up in the reaction. What it does is it tends to make it easier to break certain bonds and overcome that initial energy the reaction needs to get going. And so the reaction is able to happen a lot quicker. Now, catalysts may bring things together and join them together. It may have things and it may break them apart. It goes both ways, but it doesn't matter what it does because at the end of the day, it's not really getting involved in what's going on. It's at the end of that reaction, it's as it is at the beginning. So you can actually recover it and you can use it again and again and again. So here's a little just snippet on activation energy. Basically, all reactions are going to need a certain amount of energy to get started. If they have enough naturally, like just at room temperature to get going, that reaction could quite easily happen spontaneously. So some reactions, very little activation energy is needed. Very little energy is needed to activate it. For others, it's a lot. There's a lot of energy you have to put into it. That might mean you normally heat it up really, really hot or something like that, but that can be a really big pain. And so what we might use instead is a catalyst, and the catalyst makes it easier for the reaction to happen because it reduces how much activation energy is actually needed to kickstart that reaction. So you can see a couple of images there sort of illustrating what's meant by this. This isn't a concept that you need to know super well, but it's really handy in understanding what catalysts are actually doing. Now, I mentioned that catalysts are in our body as enzymes, but we do have them in the world around us. In industry, when they make sulfuric acid, they use something called vanadium oxide, and that helps with the production of sulfuric acid. You might notice that the catalyst is actually written above the arrow because it's not actually a reactant, nor is it a product, so you can't put it on either of those sides. So we put it above the arrow to show it was helping out. The reason they use vanadium oxide in when making sulfuric acid is it actually helps deal with the temperature and produces much more sulfuric acid at the end of the day than without it. So it's basically a cost benefit thing. It might cost a little bit of money, but there's a lot of benefit involved and actually saves them a lot of money when they're doing it. In your car, you have something called a catalytic converter. So when cars run, they'll produce gases, one of which is carbon monoxide. Now, these gases go out the exhaust out into the world, but carbon monoxide is a particularly nasty gas. It's really, really bad. So what they have before the exhaust, so between the engine and the exhaust, is this thing called a catalytic converter. It's called catalytic because it has a catalyst in it, and it converts carbon monoxide into carbon dioxide. Carbon dioxide isn't a nice gas necessarily, but it's far less nasty than carbon monoxide. So we convert it to that, and that's what comes out the exhaust. And hopefully only that, hopefully no carbon monoxide. If your catalytic converter is broken, you might actually be pumping out carbon monoxide into the air, which is very, very bad. So our last way we can alter the rate of reaction is by messing with the volume or pressure. And what we're doing here, and this tends to, like I said, be with gases, is if you compress the gas and put them into a smaller volume, you're going to reduce the space particles have to move about. And when you do that, they're more likely again to collide with each other and react. So if you reduce the space or increase the pressure, you're actually going to increase the rate of reaction. On the flip side, if you give them more space, so you make the volume bigger, or you decrease the pressure, then you're going to have a lower rate of reaction because they're all spaced out and it's less likely that those particles will collide with each other. So, like I was saying, generally this is something that's more applicable to gases because gases compress and expand a lot more easily than you're trying to do it with a solid or a liquid. So it's all down to making those particles collide and react with each other. Now, when you do react to things and you're producing something, you have what's called yield. And yield is just how much of a product is being made by this reaction. Now, you might sit down and you might calculate out what it should be, and this is called theoretical yield. So theoretical is sort of just doing the maths. If I just do the maths, what's the ideal amount that should be produced with no real world interactions in this? And it doesn't involve you actually doing the reaction. Once you do actually do the reaction, you have what's called the experimental or actual yield. And this is how much you actually produced. So the theoretical yield could be very, very high, and you might actually not produce very much at all. And some reactions are just like that. They're really inefficient and you don't produce much at all. And some are really efficient and you produce heaps. From this, you can work out what we call the percentage yield. And that's where you divide how much you got by how much you should have gotten and multiply it by 100. So what this looks like, for example, is if we only made 29 grams of carbon dioxide but thought we were going to make 36.7, well, we would go 29 divided by 36.7, and then we would multiply that by 100, and we would get 79%. Down the bottom there, they haven't multiplied it by 100, that's why it just says 0.09, but if you multiply that by 100, you'll get 79%. So, seeing that, I want you to give that a whirl on these two things. Now, I've only talked about percentage yield with grams, but you can do the same thing with moles. Just use the mole values in place of grams for the actual and theoretical yields. They go in the same places, that the formula doesn't change at all. So pause the video now and give those questions a go. Okay, so this is our lucky last slide and our lucky last question. Let's get into it. So for our first one, we want to work out our percentage yield. So I'll go percentage Y for percentage yield. This is going to be our actual yield divided by theoretical yield, so TY. So percentage yield for our A is going to be 55 divided by 160. Oops, that should be times 100 up there. Times 100. And this is going to give us 34.375%. So that's for A. All right, hopefully you got that one. For B, okay, we're going to do a similar thing. Percentage yield is going to be equal to 6/18 times 100. And so percentage yield is actually equal to 33.3. I'm going to put a above that to show it's recurring, percent. And that is the second one. It's about 33%, it's 1/3 of the yield. So that second one was not as good as the first, and they're both pretty bad ones. You only got around 30%-ish of what you thought you were going to get. So not great reactions. Anyway, that is the end of 3.9 and the end of Unit 3. Thank you for watching these videos. And remember, if there's anything you didn't understand, you can rewatch the videos. You can speed them up, slow it down, jump to the bits you need to know about. And if you've still got questions, speak to your teacher. Let them know you need some help. They're more than happy to help you. So that's all for this. Thanks for watching, and bye.